Welcome back, everybody, for the second halo on this session for today in the Cubic Hub and ABN Kiskifal Fest 2025. For me, it's a pleasure to present our next speaker, the uh, the Professor Javier Mancilla Montero, who is an expert in applied science for credit risk management, with experience as chief risk officer and director and advisor analytics in multiple financial institutions. He holds a PhD degree in quantum computing, and he's co-author on the book Financial Modeling Using Quantum Computing and QLM Unlocked, and several academic papers in quantum computing and quantum machine learning preprocessing and credit scoring enhancement. Currently, he is a CEO and co-founder of Falcon and Square Game, where it applies quantum machine learning and generative artificial intelligence to improve credit scoring systems using proprietary methods and fine-tuning LLMs. He has led the implementation of more than six underwriting systems in 5 countries and holds certification in quantum computing and generative artificial intelligence for ABM, CASE, and MIT. Thank you, Javier, to join us for today for this session and for the whole event. Just to be clear, you are completely freedom to choose how you want to present your talk in English or in Spanish. But I consider that having all the participants maybe in English will be more convenient. But this depends on you.
Thank you so much, Braulio, for the invitation. Can you hear me well?
Yeah, we can hear you.
Perfect. So thank you so much. It's an honor to be here to share uh, this journey with you guys. And yes, I'm going to continue in English because I think it's more, let's say, universal language for all came here to the Kiskit Fall Fest. So I'm going to share my screen to start the presentation. I assume that you can see now my screen.
Yes.
Yes, no?
We can see.
Okay. Thank you. Thank you. So here I'm going to talk about something that is kind of my obsession, which is the true value or how we can actually use quantum machine learning these days. Because with all of us, I think we want to avoid the hype and not talk all the time about something that could happen or something always about the future, but not making mistakes about what kind of things you can promise today or things that can be used today. So first of all, I don't think that I need to spend too much time here because it's kind of my history and about the things that I published recently, and it's about my obsession again about putting things in real businesses, something concrete, something that a bank can use, something that a fintech can use, something that even we have some recent explorations about portfolio optimization, or even in the healthcare sector, something about drug discovery even. So there is a lot of options that we can explore, but all of us are clear about the infancy of this technology, but at the same time, how we can add value with the tools that we have today. So first of all, I will start with some warnings or caveats. First of all, throughout the presentation, I'm going to simplify some of the concepts that we're going to talk. I'm not going to go through formulas and code. I'm going to share links in which I publish some of these code snippets, Jupyter notebooks. Actually, my book have a GitHub repo with a lot of exercises that you can follow. But here, I don't want to go deeper in the details of technical stuff and formulas, but more or less trying to discover with you, guide you to something that can spark ideas, and you can start looking at some of these explorations, okay? The other thing, actually the image in the right-hand side is not actually the cover of the book of Nielsen and Chuang, right? I added with AI these people being sucked by the book. So my point is that book is amazing, but could be a rabbit hole as well. So my point is that not always start from the theory or something quite complex, but trying to apply something and discover why the things are happening in certain way. So when you're trying to have the reverse engineer about how the things happen, you are forced to understand. But if you spend too much time studying, sometimes you are losing the space to actually test something in the real scenario. Okay, so don't let yourself be absorbed by Nielsen and Chuang. The other thing about the thing that should be considered, or in my viewpoint, is something that I publish very frequently in LinkedIn, for example. There's some warnings also about what is happening with the papers that we're publishing, the articles that are, I don't know, published in archive or any journal. So I don't want to generalize, but it is a big portion of the studies that are relying on toy data sets. So they're using MNIS, IRIS, breast cancer, something that eventually will not represent the reality of the market, the reality of the industries or the financial scenarios. Even with Kaggle, I'm having experience with big brands even that they are testing stuff with Kaggle, but at the end of the day, the data that they will have in the real daily basis will be completely different. So, and the model will behave completely different as well. Second, some of the studies are measuring everything in accuracy. And this is not good because if you are testing fraud detection, for example, and 99% of the data set is coming without fraud, and just 1% is fraud, if you predict all the 100% data set as a non-fraud, you will have 99% of accuracy. So imbalanced data set with accuracy is not a good match. So eventually you need to create scenarios in which you are testing with some metrics, some quantum metrics. I'm going to share that in the following slides, but also about some other metrics in machine learning, okay? Like AUC, KS, and the not only AUC ROC, but also AUC PR, precision recall. So you have several other metrics that will unveil a little bit better if the model is good or not good. The other thing is, and this is usual because some of the pieces of the academia or the private sector want to save a little bit the intellectual property. But if you are publishing a paper saying we are doing great stuff, but you don't share the code, it's quite difficult to understand if the logic is good, if the code is good, if you are, for example, doing cross-validation, if you are testing in out-of-time samples. So really having because if you having an edge of advantage, this edge can come from different places, eventually not from quantum. So from the reprocessing stage, from how you are calculating some metrics, which libraries you're using. So there is a lot of caveats around how you are actually doing your experiments. Then the other point is like compare yourself or your model with the state of the art. Don't compare QSBM with SBM because SBM is not the state of the art right now. It's good. At some point was good, but now the state of the art potentially is XGBoost or LightDVM or CatBoost or a deep learning or a neural network, for example. But it's not quite fair to compare your QSBM with an SBM because if that was the case, probably I will discover quantum advantage a long time ago because I'm constantly surpassing classical SBMs or a logistic regression. But when you compare yourself or your model with an XGBoost, the things change. The other thing is that the true progress, in my viewpoint, requires the hybrid thinking and the analysis with two models combined. We shouldn't try to grab an XGBoost and see how it goes, and grab an QSBM or a BQC and see how it goes and compare them. How if they can work together? How we can combine the distribution of probabilities, the prediction of each one of them in the real scenario, right? So how they can work together, and how we can route some of the samples to one model or the other. Can we detect data complexity, for example, check if the pieces of the data set are good for XGBoost or not? So there is a lot of different alternatives to actually analyze the potential combination between the two technologies. And complexity. I think sometimes we're trying to tackle, this happens a lot in Kaggle, which is my next slide. It's like we are seeing data sets, for example, in fraud detection, that the AUC already for a logistic regression or random forest or a gradient booster is already at 0.97, 98% in AUC. So why you are trying to have an edge of advantage there. Eventually you can, because you can have a better recall or having better precision in class 1. But at the end of the day, I was talking the other day with people from D-Wave, and they said, please don't come to me with simple stuff. We provide advantage in complex scenarios. We need a lot of complexity to actually provide something that at some point can be meaningful. So I will walk you through a few questions that I have in mind. First of all, should we compete with classical methods? And we have this picture about two boxers that one is BQC, for example, the other is XGBoost, as you can see near to the belt. And they should fight each other, or we should find an alternative. So probably you are seeing in the papers and a lot of publication this scenario: QSVM, BQC, and all the distilled versions from QSVM. We have different ways to use kernels, for example, multiple kernel learning, or having an automated genetic algorithms for creating feature maps, or we can have all the versions of QNNs, BQC, integrated with classical neural networks like Dressed Quantum Circuit, Guided Quantum Compressor. You can have a lot of alternatives. But we're comparing with SVM, with XGBoost, with register regression, with random forest, or neural networks. But how about if we find synergy? How if they can work together somehow? How if we predict over certain clusters this could be good or not? So there is a few ways to combine the models. One way is ensemble the models. This is pretty well known in the machine learning industry in general. So we predict with both, and we're trying to combine the predictions. The other, or stacking, this is another alternative. Then we have the alternative, which is the reality of QSVM. Actually, quantum is not deciding anything in the SVM. Quantum is an enhancement of the kernel representation for the classical SVM to predict. So we actually are pre-processing or enhancing information that can be used for a classical model. How about if we can create the presentation or vectorization of data, how we can pre-process things with quantum, how we can do feature selection with quantum computing. So there is a different ways to combine both. Perhaps there is pieces of data, I'm going to explain this in another slide, that could be more complex or not for XGBoost or for a classical method. How if quantum can be good at that point or not? And the other alternative, which is something that I'm going to recommend here, is we can create clusters of data and test both models in each cluster and see which is the best in AUC, for example. So this is actually is a real test that I did that I'm going to share with you in several steps, okay? Imagine you have a data set, let's say fraud detection, because it's really popular now. So step one, you pick a clustering method, anything that you have in mind. There's a lot of libraries out there to separate your data set in different clusters. Step two, you train your classical model and your quantum model with the whole data set or the individual clusters. So if you create 5 clusters, you can train with all the data set, or each of the clusters have a different model. And then you use a k-nearest neighbor to match a validation set, not your train set, a validation set, and find similars to that cluster in train, right? And see, okay, I'm going to predict over validation with the 2 models, which have better AUC, which is the one that you have at the right-hand side. You have 10 different clusters, and for each cluster, we have a selection of quantum or classical. GQC there is a guided quantum compressor. So and it's a variational classifier at the end of the day. So you can see that for some clusters, the best model is not classical, it's quantum. And okay, so if this works, we will have a few samples, a few clusters that perhaps are more complex or have a certain behavior that the quantum is better. And the other could not be the best option, so you go through a classical method. In this case, I put a baseline of 0.7 in AUC to select the clusters, because you can see that XGBoost was better in cluster 3, in cluster 4, and in cluster 7. But I skipped those because they are below 0.7. So I finally can only score 35.94% of that data set with an AUC of 0.76. But this is one example. I'm not saying that this is the definitive method to use for everything that you are trying to do, It's a good example about how you can combine both models. So the other question is, classical or quantum? Which data point is more suitable for quantum or not? How we can separate this from the beginning, or trying to combine the models to detect who is the best? So first of all, we have this alternative that I also did a few months ago. That is, eventually, there is more match between something that is close, for example, for a Fourier series, in the distribution of a sample. I pick a sample of the data set, I have a few neighbors, and I create let's say, a minimum cluster, and I'm trying to see the distribution of probabilities for each sample. So I say this is the first one, the second one, and we have this line that is going, okay, this is 0 or 1, depending if how is the close of 1 or 0 is the distribution, right? And you can see that the ones that are more in the middle or less with less spikes could have less errors. Eventually, this is better for quantum or not. So you can try to analyze these alternatives. So local Fourier fit in this case is an error of the classical machine learning that is creating those curves, and the ones that have more spikes are more complex, more overfitting. You can use a quantum method that could be more close to the Fourier series. So this is one example. And at the end of the day, what you are doing here, why you are using this? Because like I said in the previous slide, we have this clustering method. So if you want to cluster your data based on complexity or based on the error based on the Fourier series, you can create new features. And in this case, in the right-hand side below, you can see that I create new features. I create Fourier error, and I create density. So we create new features, and we cluster the data based on this, which is the chart that I have in the right-hand side above. So you can see the data is clustered by the local Fourier fit error, and you have the inverse local density, which is described there. Then you have another option. You can just analyze the complexity of the data without any quantum stuff yet, right? So you can see, okay, we have a feature separation test, borderline density, neighbor distance ratio, whatever. This is a paper, you can find it, and I think it is a code also made in R, not in Python. But you can see in the right-hand side that it describes several features or analysis of the data set. So is linearly separable or not? And here a conclusion, which we can see there, that less linearly separable training samples out of 90,000 is 22,000, and more linearly separable training samples are 68,000. So you can pick and separate both like, let's say, clusters, and we can try to analyze if quantum can be better for more complexity or not. So trying to find complexity can lead you or not, depending on the case, to a more suitable scenario. And this is the other case that is not now talking about complexity in terms of data itself. But the other problem about quantum and variational classifiers in this case is when we try to, when we reach actually the complexity of a landscape to do the optimization, we can see that we want to be more expressive with the circuits, right? We want to create more entanglement and be more quantum. If you are less, you have less entanglement, this is less quantum and more classical simulable, right? So the point is that if you have, for example, the landscape like I have in the right-hand side, probably it's more complex and you can reach a Barren plateau. So reaching a Barren plateau will destroy you. If you want to avoid Barren plateau, probably you will come back to be classical. So this is a good example that is not the case for everyone, but actually works for me with a data set that actually, when I added more CNOT gates and I had added more entanglement and more complexity in the layers, I actually receive a better AUC. But this is not always the case. But we should find ways to demonstrate that with more expressive circuits, we have the real quantum advantage that we're looking for, and eventually we will add more value to any business that we're working with, right? So in this case, I jump from 0.87 to 0.89 with a more complex circuit and more expressive circuit at the end of the day. And this is the case that is supported by the study of Marco Cerezo, which is really well known in let's say in the quantum scenario. And you can see that, of course, the paper said The research suggests that the constraints placed on PQAs to ensure trainability, avoiding barren plateaus, simultaneously make them classically simulable. So at the end of the day, what is the sweet spot, right? So we need to find, okay, we have less expressive, but we will say it's a circuit, so it's quantum. But probably we can simulate this really easy. But if we do more complex circuits, we will have barren plateaus, and we need to find the sweet spot to actually not make it so simulable and extract benefit from the entanglement. And this is a real scenario. This is a test that I did with my company with a real client in Latin America. So we had this project around credit scoring. So we need to analyze, okay, how we should use quantum machine learning. In this case, was a version of QSVM using kernels, and we were creating the feature maps depending on the data. It was a genetic algorithm that create like the best approach based on a validation set, and then produce the circuit to create the kernel at the end. And the data set have a lot of registers, but they were flagged by different, let's say, sections of the society, right? Prime in terms of financial behavior, near prime and subprime. And the best performance and the one that surpasses the classical method was just in subprime and was the most complex one in terms of the circuit versus near prime and versus prime. You can see that prime definitely is less complex, right? So the point is that, okay, actually I make something that created more benefit based on the complexity of my circuit. Third question that I want to follow in this occasion, right? So question 3, can we explain quantum machine learning black box? And this is a problem that will be more frequent in the future. When you talk with banks, when you talk with healthcare, which is like handling lives, right? You need to try to explain how it works. And this is quite complex. But there is a few alternatives, and I think probably at some point in the event, you are going to receive my presentation in PDF or something. All of the slides that have relevant information have a URL or the reference. But in this case, it's like, okay, we can have certain explainability. In this case, it's just a loop of removing and shuffling features to evaluate contribution. This is the QXAI, which is have a paper and a lot of different alternatives. Basically, it systematically selects individual input features and remove them to see how they contribute in different stages of a quantum model, for example. The objective, of course, to measure the degradation in model performance, the accuracy or any other metric that you want to use, caused by the feature perturbation. The other alternative, which is more similar in the view because it's a SHAP value, it's more classical machine learning, is like component level analysis. So you isolate different pieces of your pipeline and you see, okay, feature map, how classical data is encoded into quantum states and how they influence this encoding, how the variational circuit is operating with those features, how the optimizer is having impact from those features. So there is a way to separate components. Again, the reference is there, and I think they have a GitHub repo, so you can try to extract the influence of each feature in each of the stages. And the one thing that I love from this paper is QMetric, is a library as well, is that I don't think it's a library, probably it's a GitHub repo. They have a lot of information in the paper. But my point is that they guide you to create measurements or metrics around exclusively quantum on some that could be classical and quantum, but mainly, for example, having the circuit expressibility, circuit fidelity, training dynamics, barren plateau indicator. So because sometimes you grab the information equally of what you have in a classical method from a quantum, but you don't understand really how the benefit is around quantum or not, or if we have certain fidelity or entanglement, or we have barren plateaus or not. So ideally, you should have a separate set of quantum metrics to define, okay, this benefit is coming from quantum or not, or these metrics can guide you to make some adjustment in the model to receive better output. Question 4, quantum economic business value or not? What's that? Exist? So this is more or less a recommendation, but there is a paper published a few years ago. I think it's 2022, actually, yes, from a pretty well-known specialist and academic in this area, which is Roger Melko, Francesco Bova, and Avi Goldfarb, that created an analysis comparing two firms that actually one performed with quantum computing and the other with classical. And if they find some benefit, even if there is not quantum supremacy or advantage at all, but if they have some benefit in terms of the technology available and the expenditure that they have in energy or whatever they are using, they can have quantum economic advantage. So I will recommend to read this paper because it's really good and can guide you through, okay, how actually I can add value with quantum these days, even if it's not the best model around the world, let's say. The other is the quantum business advantage. Actually, this term is coming from, I think, a conference that Multiverse Computing participated, saying, okay, we are not worrying about that we have the best model in the world, but we are creating business advantage with the models that we have, even if it could be quantum inspired, quantum simulated, or real quantum hardware. So let's do this questionnaire, right? In your benchmarks, the quantum simulated method that you're using gives you better results? Imagine that the answer will be yes. Okay, I have a better AUC. Does it give you a speed up, better performance, or any type of enhancement? Any type? Perhaps the answer is yes. Can be implemented in your current infrastructure. So you can use AWS, Azure, on-premise, whatever you have. Yes, I can. So perfect, use that. It is quantum advantage in any sense? Obviously not, but it's a good experiment that is actually adding value. So you're adding value along the way up to at the point that we have, or until we have the fault tolerance or anything that we're waiting for a few years now. It surpasses any possible model out there. So it's better than anything that everyone can test or others can demonstrate, that this is a constant fight. No, perhaps there is a very good model that I'm not aware of, I'm not using, but the quantum approach is beneficial. And this is again, it's an example, and is done by me and of course a big team in Spain, in a fintech, that we have the challenge to build a target for a machine learning model, a classical model. So the target variable was to predict default or not default in terms of payments. So if they're going to pay or not pay the loan. So the target was not default or not default. We have a portion of the dataset that have that label, but the rest we don't have, and this is open banking. So we receive a lot of transactions from different banks of the user. So ideally, we want to create a definition of target depending on events of risk that the person can have in 12 months. Events of risk, like they're not paying their installments, they have a collections company following them in the transactions. I don't know, several different scenarios. They're not paying utilities, they're having microloans. There is a lot of options. The problem, if you want to build a good proxy of good or bad payer, depending on all those variables, you have several thresholds for, okay, this is one-time microloan, two-time microloan, three-time microloan, with certain cadency and certain combination with all the other events of risk. So we will have a lot of different combinations, like it is described there. Since we have 9 types of events, for example, 9 different thresholds, each and one of them is have a binary activation, could be or not could be in certain string of scenarios. We have 2 to the power of 81 chances, impossible. So we encode this in a QUBO problem. We run this through D-Wave, and we extracted the best combination to define 1 or 0 for the classical model. And what happened? We increased the approvals in 15%, actually near to 18%. And until now, we started this last year, we have 0 non-payments. Everyone is paying. And this 15 to 18% was rejected by the previous model. and we managed to increase the approval without increasing the defaults or the people that are not paying. So this is the best method to optimize all over the world. I cannot confirm that. Is useful? It is, definitely. Question 5, how we can continue exploring. Okay, I'm not going to, I'm publishing a lot of things in different places in LinkedIn, and I have a blog called Quantum Fighter. My book have 100 references, but I will say, please read these two. Both of them related to Maria Schul, which is amazing, and I think everyone recognizes her. First, this is a good benchmark analysis done in 2024 by his team in Sanadu, I think. The title is Better Than Classical of this paper, which is really interesting. And in the right-hand side, I think it's a second edition of Machine Learning with Quantum Computers. I think it's very complete, covers all of the things that you probably are interested if you want to pursue machine learning with quantum computers or quantum machine learning. And of course, my book is available. I made this book to start from zero. I know that some of you have experience in physics or engineering, but if you don't have any knowledge about this anyways is useful. It's QML Unlocked. It's available in Amazon, and I go through different things, but mainly explaining what is quantum, what kind of hardware we have, what could be the approaches, and start truly from zero, starting with Python and using Qiskit, PennyLane, and a few alternatives to actually grab value. And we have a GitHub repo there with 100 references that you can use to expand your understanding. And if you want to code, I have an alternative as well. I'm not publishing too often these days, but this was mainly from the last year, and I want to continue in the following months. There is a few code available there that you can extract from Quantum Fighter, and you can test yourself, install your own libraries, and see how it goes with your own CSVs and data. If you want to keep talking to me and sharing information or trying to discover something new together, I'm always available. This is the QR code with my LinkedIn profile, and we can keep talking and exploring together. Thank you so much.
Thank you, Javier, for your wonderful lecture. We have some questions for the public.
Sure.
For Lopez Saldaña Alejandra, is it possible to analyze a cluster through density functional theory, or has it provoked calculation?
Sorry, can you repeat, please?
Yeah. Is it possible to analyze our clusters through DFT or Hartree-Fock calculation?
Related to the clustering method that I was suggesting, right? So actually, the clustering method that I suggested is just one idea, but actually you can use whatever you want. My point is that find portion of your data set that could be better for quantum or not. And this is what I demonstrated in the example of the project in Latin America, when you see that certain behavior, financial behavior at that point, was better or not. The technique that you're using, the calculation, the analysis, the features that you want to create, the meta features that you want to create to analyze the cluster, to create the clusters, is up to you. But everything is possible. Yeah.
We had another question for Adriana Martinez. How can quantum computing be integrated into cloud infrastructures?
I assume that you're talking about the integration of quantum hardware in infrastructure of any company, right? So actually, it's kind of integrated with some clouds. This is available already. So we have AWS Bracket, we have Azure Quantum. There is a lot of different alternatives available. But it all depends on the complexity of your business, right? Because sometimes if you're a financial institution, let's say a bank, you don't want to send data out of your ecosystem, right? So eventually, that's why some of the like OQC and other vendors in the sense of quantum hardware, they're being installed in data centers, or they're trying to do exploration about federated learning. So you have pieces of your data and model distributed in different places, and they can have a join together to have the prediction. So I will say that there is a lot of vendors available. Most of them have really fast integration. I know pretty closely that OQC is creating an amazing work about how they can integrate with other clouds or businesses, creating plugins, modules, and but mainly there are a lot of clouds that have available access. But I would suggest always to start with simulated and also emulation. Why I'm saying using emulators? Because you before you jump to real hardware, you can emulate the noise of that chip. So trying to create quantum machine learning with what is said like quantum hardware aware training. So you can emulate first the noise and then trying to use a quantum hardware. And you can, when you really want to go through a quantum hardware, you need to probably ask for credits and space to test without cost because it can be really costly. And when you find some advantage, then you can think it's something more commercial or more definitively integrated in your infrastructure. Yeah.
I guess so this responds the next question. That is from Luis Flores. Many
Mm-hmm.
quantum machine learning models are still running on simulators. What are the main challenges in transition these models to real quantum hardware, and how far are we from seeing this at a scale?
It's not something new, right? Quantum hardware have noise. They are not all-to-all connection in qubits. They don't have all of the qubits don't have the same quality. We have fast decoherence, so we cannot create big circuits. So there is a lot of constraints about using real hardware. But also, I think even if we're trying to use simulators at the beginning and see what happens, we need to, in a certain way, forced to start using quantum hardware because we need to discover if noise can be suppressed, the errors can be controlled somehow. We can apply some techniques. We can have some benefit from the noise. For example, the case of HSBC and IBM, that they said, okay, we have 34% more like performance in a quantum hardware, but they couldn't describe why because in emulators and simulators, the advantage was not there. But using a quantum hardware suddenly is giving benefit. So I think we need to keep testing for the sake of speed and iterations with simulators and emulators because we know that the difficulties that we have with quantum hardware. But when at the same time, I recommend to trying to use them because you can discover something new in terms of how you are creating a more reliable output from a NISQ machine, or eventually discover something that plays well in these QPUs.
We have another question from Abigail. You mentioned in combining classical and quantum models instead of just competing with them. Could you
Mhm.
elaborate on a practical strategy for designing a way to route data to a quantum model versus a classical one in a real-time systems?
It's exactly what I mentioned. Of course, there is a full of options. I actually have a slide that I share. Okay, this can be ensemble, can be stacking, can be clustering, can be data complexity. But eventually, let's make it simple. You have two models, right? You predict over a certain validation set. Okay, you said, okay, this is the prediction from quantum and this is the prediction from an XGBoost. Probably both of them have some errors against the ground truth. Some of them are predicting well. The XGBoost is having an error in, I don't know, 1,000 data points. And quantum is predicting good over those that XGBoost have errors. So you can discover, oh, probably there is a complementary way to do this. And if you find a way to cluster those samples that XGBoost have always errors and quantum is better in predicting those, you can say, okay, I'm not going to apply at the end of, I'm not going to infer or predict over the whole data set. I'm always going to predict over the ones that probably XGBoost is struggling with. They have errors. So you can have a router. So you can say, okay, this sample is going to who? Okay, it's classical because have the patterns of an XGBoost, better XGBoost. Or no, this is the have pattern of quantum method because usually XGBoost is failing. Or we can use all the methods that I described. So you can cluster the data previously and said, okay, I'm going to predict over those clusters and check in which cluster the quantum is better, or trying to analyze data complexity and find complexity that could be linked to a quantum model. And you can think in other options as well.
We had another question from Luis. In your experience, what is the biggest practical challenges when you implement quantum machine learning in a business today?
I think the I think the approach of all the project needs to go through an analysis first, because some companies wants to just put the quantum name in the project, but the complexity is not there. You have good classical models to execute and have results. So just for the sake of, oh, I'm exploring quantum, or I have a great partnership with certain brand, this is enough. But I would say that you need to find real complex scenarios. This is what I'm suggesting in my presentation. Find cases or pieces of the data that actually could be more convenient for quantum, and trying to apply this there. So if there are so many people trying to apply quantum all over the place, or like doing research with toy models, but when you're trying to apply this, it's not working in real scenario, this will make it more difficult to actually grab a value from every test and every exploration that we actually want to do. And of course, the inherent problem of all this journey about applying things is the hardware. So we are kind of linked with the hardware. So if the hardware is better, we can try to do better. And the third or fourth thing, I don't remember now, is the lack of algorithms. We always playing with the same stuff for QML. So we have QSBCs and all the 100 different approaches around that. We have BQC and a lot of, at the end of the day, we're just creating kernel and new loss functions, but we're not inventing any new algorithm. So, and well designed for quantum, like Shor's or Grover or others that created something quite specific for quantum computers. So I think we need to try to invent something. This is something Maria Schultz shared in a presentation, which is available on YouTube. And she said, we need to address the elephant in the room. So we are trying to play with certain things that could not be working properly. And we need to find a new way to actually grab advantage of what can be quantum computers.
Fantastic. We had another question for Jose Gabriel Castillo. I had a position as QA test automatization. I want to move to this new area. Currently, are there QA teams in charge to validate the quality in quantum systems and quantum machine learning? Or do you use a different paradigm in the methodology for quantum development?
I'm not sure if I follow the question, but it's around how I can measure the models or how I can analyze the models. I'm not following. Sorry.
It looks like he tried to ask, for example, for the QA teams about what it will be validation, equality, and quantum
Exactly.
system and quantum machine learning. Yeah.
Yeah. In terms of QML purely, is what I just shared. So we have the classical machine learning methods that you should use. Please, no more accuracy, not alone at least. And you can add the quantum metrics. So Barren plateau, fidelity, you will have a lot of indicators or indexes that can allow you to understand, okay, more entanglement, less entanglement, things that can allow you to understand better. In the sense of hardware, there is let's say a discussion about what is the consensus around which is the best metric. There's something that IBM came with, which is the quantum volume. So there's a lot of alternatives to analyze, okay, this is the error that actually a quantum computer is having. But I think more in the QA side, you will not always analyze the hardware itself. Always, of course, you need to, but you will analyze how your model perform under this chip. And you can have all these metrics. Actually, if you have the presentation later in PDF or whatever, I put the link there so you can go through these new metrics that are not only the classical ones.
Okay, we have another question. Given the economic diversity in Latin America, how could quantum machine learning contribute to more inclusive and transparent credit systems?
Yeah, this is a very good question, because I remember another discussion. I participated in a conference with the European Banking Authority, and I know that the discussion is around Latin America, but let me explain. The European Banking Authority said that if you always need to be explainable in the sense of credit scoring, and this is the key for any regulation. Eventually, even in some countries, they are requiring for people that are rejected, you need to explain why, even if it's a machine learning model. And with the AI Act in Europe, you need to also be careful about warning the user you are being analyzed with an AI. But the problem is that even the European Banking Authority, or the problem or the benefit, said even if you don't have the explainability, but the increase in performance is quite high, this model can be allowed, right? Because it's about financial inclusion. Because if you are rejecting 20, 30% of the users because the model is underperforming, and you include quantum and you approve those 30%, and actually they're paying on time, something is good, right? And now I'm thinking Latin America. We have a lot of underserved people in terms of banking and credit. We have a lot of people that don't have banking access at all, but you can include some data sets. Always the data is, without data, we cannot do anything, right? But assuming that we have certain data, even data that is not classical, not just financial behavior, but could be social media behavior, another thing that you can grab. And using quantum computers, that can give you benefit. Anyway, like I shared here in my presentation, there is a few ways to give explainability by the pieces of your pipeline, or by the analysis of how you are kind of adding or removing a feature over your whole pipeline and see if they have certain influence in the result or not. So there are options, but this is definitely something open to research. That's my viewpoint.
Okay, we had another question from Luis Flores. If the goal is real world impact, are we focusing too much on chasing a quantum advantage instead of building useful hybrid systems today?
If I follow the question, is are we pursuing too much quantum, or we're trying to provide benefit, right? Something like that?
Yes.
Yeah. So my answer, I think, is, again, is part of my presentation. It's like, I'm not so worried, to be honest, these days, because we don't have the computers, the quantum computers that we need. I'm not worried about quantum supremacy. I never will say quantum advantage at all. We can say quantum business advantage, quantum economic advantage. We can say this is beneficial for me in my current stack of models. That's it. I remember a dialogue with a bank the other day in Europe, and they said, why you are using certain model or not? Because I tested some classical methods. I used it and tested these other quantum methods in terms of optimization, and the best result was coming from quantum. Oh, but there's another alternative that is classical and good enough. Amazing. I don't have the knowledge to use that, or I was not aware that this method exists. So for now, quantum for me is good. So also it's a way to try to play with these tools. And at the point that we have benefit with the hardware, the jump from trying to do something that could be meaningful today to what actually you can run in a quantum hardware can be more direct than not doing anything at all for 2, 3, 4 years. Your people are not trained, and you can actually jump from zero to a quantum hardware that at some point we can have this ChatGPT moment that everyone will try to use a quantum hardware potentially, let's say, in 5 or 7 years from now.
Okay, we had another question. What skill or backgrounds do you think young professionals should focus on contribute meaningful to the field of quantum machine learning in the next few years?
You mean the kind of professionals and profiles?
The profiles, the backgrounds, the skills that they need to develop it.
Yeah, I think some point when everything starts, not everything, like when the curve of hype starts really deeply, potentially around 2018 or something like that, everyone should be a PhD, everyone needs a physics background, everyone needs to be like the Nobel Prize type of guy. But now I think we are lacking from software engineers, data scientists, even DevOps that actually can play with the tools about quantum computing and quantum machine learning. Even people that I know, for example, one of my colleagues is an amazing data analyst, but he was a dancer a few years ago, and and uh, and, and I know a lot of people with different backgrounds, but if if they are passionate about what they want to do, they definitely can contribute. Also, you have let's say the soft skills around quantum. It's about understanding the technology, make others understand the technology. We need sales team for the vendors, for the new companies about QML. We need different like project managers that understand the technology as well. So you have different profiles that I think will be expanded along the years. But my recommendation is probably people coming from different places. But let's say software engineering, data scientists, they can easily start using IBM Quantum, Qiskit, trying to play with the tools that are available and extract some nuanced benefits that can grab from there.
Okay, and then so we have the last question. How do you
Mhm.
combine decision makers in finance to invest in quantum approaches when classical methods are still strong?
Ah, question is less related to QML, more related to optimization, for example, for portfolio optimization.
Portfolio optimization.
Yeah, for example, the other day I was testing with this new technology coming from an Extropic thermal. Remember that they have a new thermodynamic chip. It's something is created by people that coming from quantum. And I test a few stuff about portfolio optimization, right? And also with QAOA or any other method that could be for optimization. Of course, some of them are quite limited because you cannot encode 500 different stocks over the whole year and trying to predict over the next one because we need more qubits, right? Especially in QAOA. But what I saw is that even the classical methods are really good, even if they're really good and the predictions are better, some quantum methods can give you an extra at the point that you are taking the decision because you can define that the model can have more diversity, and creating diversity could be really complex. So if you, for example, in 2024 or 2025, if you are betting on technology, Nvidia, Tesla, Microsoft, right? This is a secure bet, and probably a good model will tell you, okay, you should follow these guys because it's working. But I tested that using quantum, you can have a more diverse portfolio with healthcare, with finance, with other sectors that provides you even more profit, but with more risk, right? Because it's less secure and more diverse. So I was talking the other day with a company, an hedge fund, that they said, okay, this is great because we are still investing in Tesla, right? And in Nvidia and the things that are more secure. But every time that we are going to invest, I want to check with Quantum and see, okay, this is the secondary portfolio that could be interested because the combination is more complex and blah, blah, blah. But you can have this other portfolio. Okay, I'm going to use 20, 30% of that diversity and include that diversity in my new portfolio for the next day, hour, or let's say months, right? So this is an alternative. Always trying to look at, again, with QSBM, really harsh scenario. It's like we are not replacing the SBM. We're just providing different spatial, let's say, distribution of vectors of the data that is coming for the SBM to take the decision and draw that hyperplane. So it's just enhancing the capacity of what we have. Let's not trying to replace the whole thing.
Okay, and this is a very personal question.
Go
What
ahead.
could be your best advice for all the Latin American persons who want to jump to the field? Do not be scary about when they hear the word quantum and competing together. What could be the best advice for them to really
I,
want push a career on it?
I think we should I think we have a human professional capacity and let's say an impressive capacity, let's say, because I know a lot of people from Mexico, Colombia, Chile, Brazil. They are full of researchers and institutions working around this, and we have the same capacity that everyone in any part of the world. It's just a matter of us to actually put the hands on this stuff and try to produce something meaningful. because I will not say, okay, Chile will have a brand new quantum computer fabricated by us. This is not real, or Argentina or Colombia, because this is kind of related to the big ones. Even we can do some tests, and amazing if we can do that. But this is more related to Europe, or more related to China or the United States, or even Japan, right? But I will say that our contribution to this world is like our human capacity, our intuition, our creativity coming from Latin America. Is really the kind of guys and women and men that are related to a community of Latin America. We have a certain tone, a certain way to do things. And I think we have this power to give value to the whole quantum ecosystem from the human side, the professional side, not necessarily through hardware. But if any of you or people that are working around hardware, please continue. It's definitely a good option. But we have a lot of human power in Latin America. Let's use that and let's add value to the whole world. Yeah.
Thank you, Herbert. Thank you for your wonderful lecture, and thank you for really accepting our invitation.
Thanks
And
to you.
show you guys your work for all Latin America and also Mexico as well. It was a wonderful opportunity to have you here like a speaker. And thank you so much for the Cubicle team to accept on the invitation.
Thank you, Braulio. It's an honor, and I hope we can continue with these activities. I think it's amazing, and the people that came to this, let's say, virtual conference, thank you for being here and be part of this journey. Thank you so much.